Typical problem in geostatistics. Missing data prediction from samples to prediction points. Nowadays massive data are collected by remote sensing with missing values due to obstructions, satellite paths, equipment malfunctions, etc. Challenge. Efficient and automatic prediction of big data. Classical geostatistical methods. They have favorable statistical properties, optimality, linearity, and unbiasedness under ideal conditions. But they are computationally intensive and prohibitive for large data. Complexity increases proportionally to the third power of the data size. They require human inputs. Variogram model, parameter inference method, Kriging neighborhood. They typically assume multivariate normal distribution, assumption often not justified by the data. Need for new efficient methods. We propose the Ising nearest neighbor correlation method. Let us consider a set of variables Si on a lattice, where Si equals +1 or Si equals -1 and the Hamiltonian, where Jig, exchange interaction between nearest neighbor nodes I, J, Hi, external magnetic field on site I. Further, for simplicity, let Jij is identical to J and Hi equals 0. Boltzmann-Gibbs probability density function, where effect of the model parameters Jt. Statistical physics. Geostatistics, inverse problem. We assume partially known data. The task is to estimate model parameters by maximum likelihood. Then, an optimal estimation of unknown values in locations GP can be obtained by maximizing the conditional PDF or minimizing H with respect to the unknown values. Spin models, problematic parameter inference, partition function intractable already for relatively small number of data n. Solutions. Various approximations. Bayes approach. Non-parametric approach. Non-parametric approach is based on matching normalized correlation energies of the sample and of the entire grid. Optimization problem, minimizing cost function that describes the deviation between C and CS defined as constraints, local, known data, global, correlation energy. Optimization task, find spin configuration that complies with both local and global constraints. Set the increasing vector of thresholds TQ. Discretize sampled data according to T1. Calculate the sample correlation energy CS based on SS. Assign initial values to the spins on GP. Calculate initial values of C, 0, and U, 0. Assign spins on GP with value -1, label 1 and include in GS. Repeat the above for the remaining levels. At the end, all SP are assigned one of the Q labels. Soil quality data. NC equals 7. Superior performance of INNC. Surface elevation data. Superior performance of INNC. Surface elevation data, NC infinity. Superior prediction performance of INNC for smaller p. Superior computational efficiency of INNC for all cases. Superior prediction performance of IDW for larger p. Tests on synthetic data. Gradual decrease of misclassification rate with grid size. Only linear increase of CPU time with grid size. Proposed non-parametric INNC method for spatial prediction of data on Cartesian grid based on Ising spin model. The INNC algorithm can be used with labeled data, as well as discrete and continuous real-valued data. Advantages: universal, no assumptions about data distribution. Automatic, no user input required. Efficient, suitable for large, remote sensing data. Accuracy, competitive with other methods. Further directions. Further substantial increase of efficiency, highly parallelized implementation on GPU is feasible due to short-range interactions. Extension to irregularly spaced data, achievable by defining the interaction constant jig via kernel function.